since you just have a sum of all the spins, what you're doing is now the interaction is gone. The interaction is replaced by the average value, and then now the system consists of independent spins, all of which, each of which sees the average spin value of the neighbors. Okay? So now this is a single particle problem. Although you started off with the n number of particles, spins, magnetic dipole moments, which interact with each other, you have simplified the problem, so you just have n number of independent spins, except that they see this average neighbors. Okay? All right. Now it turns out the mean field approximations in general, in magnetism in particular, if the dimensions of the lattice is larger than 3, of course this exists only in a theory because we live in a three-dimensional, spatial dimensions, but you can show mathematically if the dimensions are larger than 3, only even by a small amount. It doesn't have to be exactly 4. If you're a theorist, you can talk about 3.01 dimensions and 3.2 dimensions and such. As soon as you go over 3, mean field approximation is known to be exact. It's no more approximation. But if the dimensions are less than 3, then of course this is approximation. And the lower is the dimension, the poorer is the approximation. In one dimension, it's a very bad approximation. Very bad. It's 2 dimensions, it's pretty bad. In 3 dimensions, not so bad. Okay? Although it's not so bad, if you look at details, you find that the mean field approximation differs from the exact calculations. Exact calculations are often very, very difficult to do. You can do higher order approximations. You can compare with this. Or if you have only small number of magnetic ions, magnetic dipole moments, then you can put it into a computer and you can do exact numerical calculation. But it's different from the true system in which you have a large number of magnetic moments. Or you can do experiments and do measurements. And then you'll find that the mean field approximation gives you results which are qualitatively okay, but exact temperature dependencies of various quantities, and those are wrong. Okay? So in that sense, even in 3 dimensions, is not a very good approximation. As I told you, this is the lowest order approximation from which people do a better job. They do better approximations starting from here. Yes, so much for the remark. And you notice immediately this quantity, because we're using unit of not h bar, but dimensionless. Therefore, if you take the average spin, average value of the spin of magnetic dipole moment, and multiply that with g, and multiply by mu b, and you have 1 mole of such magnetic dipole moments, then that's the molar magnetization, right? Right? Because there may be the individual spins at any given time may be pointing in all kinds of directions, but if you add them all, that's the magnetization, right? Divide by the number of particles, then it's the magnetic dipole moment for average magnetic dipole moment at for each ion. Therefore, it should be that. Why? Because this is dimensionless. So if it's completely polarized, if a given magnetic dipole moment is pointing all the time in one direction instead of fluctuating, then this value is 1. Why? We forget the direction. It's 1 in some particular direction. See, okay? That's our unit. Okay? We're not using a unit of h bar. That's why magnetic moment is spending all the time pointing in one direction at 1. Now here's another point. In reality, if you look at a spin quantum number, So if you look at the expectation value of a spin operator, and if you look at the z component, okay, then it can be, let's say, s times h bar, s minus 1 times h bar, blah, 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 minus s times h bar, right? But we're going to make this 1. Okay, most people make this 1, right? Even if the spin quantum number is 1/2, we use the full value 1 in many cases. If you don't like it, as I do, then I'm going to put s value here. So divided by s. I'm going to divide it with the spin quantum number, right? What am I doing? No, this is okay. All right. If I did that, then you have to multiply this with s, right? So some people do. So watch out. Okay? But here I'm not going to do it. So I'm going to maintain the spin quantum number s, right? Okay. So using this, observing that, you can rewrite that in the Hamiltonian. So it's minus z times j times s, which we replace with molar magnetization divided by Avogadro's number and the g factor of the ion and the Bohr magneton. Then sum over I of, okay? So this is the approximate Hamiltonian. And Zj. Good. Now we're going to apply magnetic field. B. Then, of course, magnetic moments want to be in the direction of magnetic field. But remember, for convenience, we have chosen the direction of the spin, which could be the total angular momentum or spin angular momentum if the orbital angular momentum is negligible. They are anti-parallel to each other, but we have chosen them to be parallel to each other. Therefore, we say the spins want to be parallel to the direction of magnetic field. Okay? If you're careful with the sign, then you said dipole moment wants to be parallel to the direction of magnetic field, and the spins, or J, total angular momentum, wants to be anti-parallel to each other, right? But we don't care. We chose the sign. We are dealing with electrons whose charge is positive to make our life easy. Therefore, if you apply magnetic field, then you have a minus instead of plus, G times mu B times S. This is the magnetic dipole moment. Times the magnetic field, okay? We have a negative sign because we have chosen S and the magnetic dipole moment to be parallel to each other for convenience, which many people do. Okay, so now if you look at this, then you can see, this term is essentially the same as the magnetic field, right? Because you can rewrite this. Because B is constant, I can pull out B in the front. Okay, there's a dot here. All right? So this term plays the role of additional magnetic field. That's why historically this approximation is called mean field approximation. Interaction is you do a first order approximation of interacting particles, then the essential part of the interaction now plays a role, which is the same as the role of the magnetic field. That's why it's called mean field approximation.